In this recording, we will talk about how to use the computer to do various correlational analyses. I want to start with showing you something very simple in Excel. This is something I actually use a fair amount that's just useful to know. And we can use Excel to go from a correlation to the Z transformation of that correlation, and then we can even go back to the correlation itself. So let's just make these columns bigger so we can see the headings easily. So let's just type in a couple correlations. Doesn't matter if you type in the same thing that I do. Just want to show you what this looks like and how it works. So let's do those. And now we want to do the Z transformation of that correlation. So click in the box where you want the new value to appear, and then click on Formulas. And it doesn't show up nicely here, so we have to go to More Functions, Statistical, and Fisher. And then we tell it what cell to use. So in this case, we're going to want it to do A2. Click OK, and you can see here, X is the value for which you want the transformation, a number between -1 and 1, excluding -1 and 1. So it has to be within the range of a correlation. And so 0.23 doesn't change very much. Remember, small correlations only change a little bit when we do the Z transformation. But these bigger correlations are going to change more. The easiest way to do that is just to click on the lower right-hand corner and pull that down. And that will fill in that formula for the cells below. So 0.56, the Z transformation is 0.633, -0.84, -1.22, and 0.47 changes to 0.51. One of the ways that you often use Z-transformed correlations is to average a set of correlations. So we want to find the average of this set of correlations. We could, I suppose, it wouldn't be right, but we could just simply average them. Hit return, and the average is 0.105. But that's not a good practice. It's better to transform to Z first, average the Z transform correlations. So we'll just go back up again to auto sum average. Automatically selects for us those 4 boxes on top. Hit return, 0.039. And now we can take this average of the Z transform correlations and transform those back to R. And we do that by doing the inverse Fisher function. So we go to More Functions, Statistical, and Fisher Inverse, right below Fisher. And then select the appropriate cell, so B6. Click OK. And then the transformed is very similar because the correlation is so small, it doesn't change very much at all. But notice that 0.04 is possibly importantly different from 0.10. That's because we use the Z transformation. So just a quick way to use Excel with correlations. That's all I'm going to show you in Excel. We're going to spend the rest of our time talking about R. So let's open up R. And let's load our commander, because that's where we will start. Okay, so here we have our window. Let's make it bigger. And then we also need to load the HSOUR2 package, because we're going to be using a data set within that package. Just going to put that over there. So first, let's load our data. So data in packages, read data set from an attached package, double click on HSOUR2, and the data we want is called US air pollution. Double click on that, and let's just click on Help on Selected Data Set to learn a little bit about what these data are. So air pollution data across 41 US cities. These data were collected in 1981, so it's been a little while. This is a data frame. We have SO2 concentrations, average temperature. MANU is the number of manufacturing enterprises. Population in thousands from 1970. Wind in miles per hour. Precipitation in inches. and pre-days, average number of days with precipitation per year. What this data set was used for was to predict SO2 from these other variables. Okay, so that looks good. So go back to our Commander, click OK to read in that data set. Now we can view the data set. So we have U.S. cities in our first column, and then the variables. We have 41 rows and 7 columns. So the first thing we're going to do is to look at the data, and we'll do that by using scatter plots. So if you go to Graphs, Scatter Plot, notice there's Scatter Plot and Scatter Plot Matrix. We're going to start with just Scatter Plot, which allows you to look at the scatter plot for just 2 variables. So let's select SO2 for our Y variable, because that's what the data are designed to predict, and then let's pick Manu for number of manufacturing companies as the X variable. And let's start by just looking at what the default scatter plot looks like. Click OK. Now your scatter plot is going to open up in your R window, not within our Commander. Okay, so here you can see that in the scatter plot we get several pieces of information all in one scatter plot. So we get the open circles are the actual data points. We also get the least squares line, so our straight green line. This would be the regression line, essentially. There's also a smooth line, which is the solid red line here, and that's locally weighted. So the line is drawn across these different portions of the data. And this is used to look for deviations from linearity. So we have this funny downward trend at the beginning. We have another downward trend here. There's some strange things going on at this lower end of both variables. And then the dotted red line shows the span around the smooth line. And then we have pretty simple box and whisker plots on each of the axes that show us we have a couple of outliers on the high end for both variables. Okay, so that's what we get by default. Let's look at some of the other options we have. So let's go back to Graphs, Scatter Plot, and now click on Options. So jitter, the X variable and the Y variable, this is a pretty helpful aspect of R. So right now, if we have more than one data point that falls in exactly the same spot, it only looks like one. If we jitter, then the data point is moved just slightly off to the side so that we can see all of it. If we wanted to use log transformations of values, we could click these boxes right here to do that. Here's our marginal box plots. If we didn't want those, we just uncheck that. And maybe we don't want the smooth line, we just want the least squares line. We want something that looks a little bit cleaner. Span for smooth, that is the span that is used to determine the smooth line. So if we kept this in here, maybe let's put this back in here to see what's going to happen if we increase that span. Let's increase it to 80. So now it's going to have bigger chunks that span is over. And then we can identify points on the scatter plot, either automatically, like it did here, where it identified some of the outliers like Providence, interactively with a mouse, so we can click on them and identify them. Let's choose that and see what that does. And then do not identify. You just get points, but no identification, and then number of points. You can choose how many points that you want to identify. You can change the labels quite easily. Right, so the X label, we want to call that manufacturing. Y label we want to call SO2 concentration. We can give the graph a title. We can also change the size of our points. We can make them bigger or smaller. We can change the axis text size, so we can make the numbers bigger. We can make the text labels bigger. They look kind of small. Let's see what those look like. I don't know, 1.7. Choose something else. You can see what else it looks like on yours. So now let's click OK. So this is telling us use the left mouse button to identify points and the right button to exit, because we chose that identify with the mouse. So now here is our new scatter plot. Right? We said we didn't want box plots, those are gone. We wanted bigger labels, probably too big now. We should go back and adjust those to be a little bit smaller. Here's our regression line, that hasn't changed. Our smooth line looks different now because remember we changed the span to be bigger, so it's not being influenced as much by some of these smaller points. Maybe we want to know what these smaller points are, so let's click on this really small one. Which city has few manufacturing companies and a pretty low SO2 concentration? Well, you can only see part of it. That's tricky. I guess you could compare this to the data and see what ended in HITA. Let's try one that's right on the smooth line, Minneapolis. Okay, so we could choose as many as we wanted. This one looks kind of high. What's that? Philadelphia. All right, here's another low one, Des Moines. And then once you want to be done with that, then you right-click and click on Stop. And then it brought us back to the scatter plot. That's interesting. So we can go back to data now. One more thing that is useful is this plot by groups. So if you click on it now, nothing happens because all of our variables are quantitative. We don't have any categorical variables here. But if we had a categorical variable, maybe if they were split into different regions of the country, we could plot by groups and get a different scatter plot for each of those groups. So that can be pretty helpful. You can also use a subset of observations. So let's say we only wanted to look at manufacturing that was less than a certain level. So we only wanted to look at this lower end. We wanted to not get concerned with these outliers. So maybe we only wanted manufacturing to be less than 1,000. Click OK. So now this only goes up to 800. At the lower end, this is interesting, that because in our previous graph, it was a pretty steep line, but now if we're at the lower end of manufacturing, now our correlation is pretty small. This is actually an interesting demonstration of restriction of range, which we talked about in class, that oftentimes if you restrict the range, so we got rid of the higher points over here, restricted our range just for manufacturing, now our regression line is much flatter. Okay, another thing you might want to do, you want to be concerned with more than just two variables. You want to look at how several variables correlate with each other. That's what the scatter plot matrix is for. Now we have to select three or more. So let's select manufacturing and then click on control to select more, population, SO2, and temperature. We want to look at all of those. We can look at our options again. So we can get density plots. So now we're going to have a diagonal. We can look at different things on the diagonal. Density plots, which is similar to a histogram, and it's a good way to view the distribution. It's a good way to view the distribution for a particular variable. We can get histograms, box plots, one-dimensional scatter plots, which are not very useful. Normal QQ plots, where Q stands for quantile, and this compares the distribution of a variable to the normal distribution, which is the straight line, which is a really good way to look at linearity of the data. Other options, you can have a least squares line, so this green line. You can also ask for a smooth line. Let's take that out just so it's not so busy. You can show the spread of that smooth line if you want to. You can add a graph, all kinds of things. So let's click OK. So here's our matrix. So we have each variable crossed with all the other variables. This is what those density plots look like. So for all of them, they're positively skewed. And then we have each variable crossed with every other variable. So this is manufacturing and population. Look how close these data points are to that line. That's going to be a really strong correlation. Here's one that's pretty spread out, SO2 and temperature. So temperature is less strongly related to SO2. And now let's see what that looks like. I want to show you what the QQ plots look like. So let's go back to graphs, scatter plot matrix, and in our options, let's just do 3 now. Let's do SO2 with temperature and wind. So for our options, let's look at those normal QQ plots. Click OK. So here's the QQ plots on the diagonal. The green line is where you would expect all the data points to be if the data were exactly distributed in a linear fashion. So temperature looks pretty good, wind looks pretty good, SO2, we've got some outliers both on the high end and on the low end. So in the middle, it's following linearity very well, but not on the extremes. Okay, so now that we've looked at the data in terms of the scatter plots, let's actually calculate some correlations. So we go to Statistics, Summaries. Let's start with Correlation Matrix. And so we can pick 2 or more, so we could just do 2. But let's look at this one, SO2, temperature, and wind again. SO2, temperature, I'll hold down the Control key to get more than one, and wind. We can choose which type of correlation we want. Pearson product moment is the default. That works for these data because they're all nice quantitative variables, but we can also do a Spearman rank order, and we can ask for partial correlations, which we haven't talked about in class yet, so we won't worry about that right now. And then which observations to use, complete observations. So this will only include observations for which every single data point is available, or pairwise complete observations. So this way, if you have at least the 2 variables within the correlation have data, then it will include it. So if you had data for SO2 and temperature but not for wind, that data would at least be included in the SO2 temperature correlation. Whereas if you choose complete observations, that would be kicked out because you didn't have everything. So I prefer the pairwise. You don't lose as much data. Oh, and here we can choose pairwise p-values. That will certainly be helpful. So let's click OK. Now here is the output. So here's what the script looks like for that. The Pearson correlations come at first, every variable with every other variable, so the diagonal is always going to be 1 since it's correlated with itself. SO2 and temperature, negatively correlated, very small correlation with SO2 and wind, and then temperature and wind also negatively correlated. Tells us the number of observations, that's always useful to know. Here's our 2-sided p-values, so 2-tailed p-values. You can see for this correlation and this one, those are below the typical 0.05 cutoff, but SO2 and wind is not. And don't worry about the adjusted p-values down here, just use these pairwise 2-sided p-values. And if you want to get p-values for just 2 variables, the other thing you can do is Statistics, Summaries, Correlation Test. So if we want to look at just SO2 and manufacturing, we can again choose which kind of correlation we want. Now we could do a Kendall's tau if we chose to. The alternative hypothesis is either going to be 2-sided, so your 2-tailed p, or that the correlation is less than 0 or greater than 0, so the 2 options for a 1-tailed p-value. Let's keep it with the 2-tailed. Click OK. So it gives you the t-value, degrees of freedom, and the p-value, and tells you which alternative hypothesis you chose. So the non-directional 2-sided is what we chose. This is nice. It gives us the 95% confidence interval for the correlation, and then our sample estimate, 0.65. So this gives us a lot more information than we get from just the correlation matrix. Okay, so that's what we're going to do through our commander. The rest of what we're going to do with correlation, we're going to do through the script. Let's open our studio. And we want to open a file. We'll open our script file. I have it in my Lab 4 folder, correlation syntax for R. Now it creates that script window for us. Yours might have this piece showing. I often just hide that if I'm not using it because it gives me more room to see my script and my output. So the first thing we need to do is to load the data. RStudio and the R we had open before don't talk to each other, so we have to open it here too. If we try just to attach US air pollution, click Run, it tells us there's an error. It can't find it. So first we need to load the data into RStudio itself, which this first line will do. So click Run. Now we can attach it. All right, that worked fine. It said there's something masked from the package, precip, don't worry about that. If we want to look at the structure of the data, we can do that. So a data frame with 41 observations and 7 variables. We have integer values and numeric values. So let's start with the very basics, just to calculate a basic correlation between two variables. So in this case, a correlation between temp and precip. Run that. We get our correlation output here, 0.386. Do the same thing for covariance. So COV instead of COR will give us the covariance between those two variables, 32.86. Now we want to calculate correlations for all variables in a data frame or matrix. We don't want to just do two variables or even a subset of the variables. We want to do all of the variables. So let's start by looking at the correlation matrix. We can also do a covariance matrix. So the data set we want to use is the U.S. air pollution. Use equals. What this does is it tells R how to handle missing data. So we've told it to use pairwise complete observations. So this is the same thing we did in our commander, that as long as both of the variables in a pair have data, it would use that. Other options are all .obs, which means there can be no missing data, and complete .obs is a listwise deletion. So if one variable has something missing, then it's going to get rid of that data for all of those correlations. We also have a method option, which is the type of correlation we want it to calculate. So in this case, we want it to do Pearson. Other options are Spearman and Kendall. And this is optional. This is the default, so if you don't want to include this piece, you don't have to. Let's include it to begin with. And here is our matrix. So again, 1's on the diagonals, and then every variable crossed with every other variable. And let's just look and see what happens if we take out these last two options. So if all we say is COR, U.S. air pollution in parentheses, we get exactly the same thing because what we had there before were the default options. Okay, we can do the same thing with covariance. So now we get the covariance instead of the correlations for everything crossed with everything else. All right, so oftentimes you don't want to correlate every variable in your data set with every other variable. So there's other useful ways to go about just correlating some variables with another subset of variables. So first we're going to create two new data sets, X and Y, and in X we're going to put from U.S. air pollution variables 1 and 2. So the colon basically means through, variables 1 through 2. And if we go back up and look at the data, or actually let's do head U.S. air pollution. This will tell us what our variables look like. So SO2 is the first variable and temp is the second variable. So we're putting those two variables into something called X. So if we run that, it doesn't do anything because we just put it into X. If we highlight X, we can see that that has SO2 and temp for all of the cities. And then we're creating a data set called Y that has variables 3 through 7. So manufacturing, population, wind, precipitation, and precipitation days will be in Y. Run that. And now we can say correlate X, comma, Y. So now we're correlating the first two variables with the remaining variables. And here now we're getting just the correlations we need, which is much easier to deal with than something like this that seems a bit overwhelming. And do the same thing with covariance of X and Y. You get just those two variables with the others. Okay, now we're going to calculate correlations and covariances with significance levels. So here we're just getting the correlations with the covariance. We don't know what the p-values are. We don't know what the confidence intervals are. There's lots of things we don't know from this information. So in order to use these commands down here, the data structure has to be a matrix, and it only uses pairwise deletion. And this is within the HMIS package, so we have to load that package first. Now we need to convert the data to a matrix and calculate the full correlation matrix. So we can do that all in one step. So that's what this piece does. As.matrix forces US air pollution, which is a data frame, into the matrix structure. So let's view the data so we can see what it looks like. So view with a capital V, US air pollution. If we run that, it will open the data set for us in a new window. We can see what it looks like. Now if we ask it to put it in terms of a matrix, so run just that as.matrix piece. Now when we view it, it looks the same. Right, so it doesn't look any different, but R is using it in a different way. And so it doesn't really impact us, it really only impacts R. So now we want to run our core on this US air pollution matrix. So click run on that full line. And now we've got the first part of our data here. These are the correlations, sample size, and now here are the p-values. So everything crossed with everything else for the p-values as well. We can also do it for just pairs of variables. So our core temp precip gives us just those two variables. So 0.39 for the correlation, 0.0126 for the p-value. Now we can calculate correlation and covariance for different levels of a categorical variable. So we haven't done this yet. We didn't even do this in R Commander because we didn't have the right variables, right kinds of variables in the data set we were looking at, although you could easily go back and do that. So we're going to do a different data set, the Cowles data set in the car package. So let's load that and attach it. And if you want to know what that data set is like, you could do a quick search. Cowles data set in the car package in R. Let's see what this does. So this brings up a PDF that talks about this package. Let's search for, I just say Control F, Cowles. Okay, so it tells us it's on page 38. Click the down button, see if we can get there easily. Okay, so here we are. Cowles and Davis's data on volunteering. So the Cowles data, this is a big data set, 1,421 rows. Study of the personality determinants of volunteering for psychological research. So we have, this is, data includes neuroticism, extroversion, sex, and volunteering. So this is why we're using it, so we can get a factor variable, so we can actually look at things by groups. So back to R. So we are going to load yet another library. It's kind of a big library day. This library is called Plier, P-L-Y-R. Really useful way to rearrange data. And the name of the package is from like a pair of pliers, like the tool that you can move things around to how you want them to be. And there's all kinds of really great functions within Plier that start with two letters and then ply. And the letters stand for the type of input you are using and the type of output that you want the package to create. So since this is ddply, we know that the input is a data frame, so the D comes from data frame, and the output is also a data frame. So we have two data frames for input and output. You can do all kinds of different structures, and then you could have different letters here. So we look down here, ddply is what we want to use. Cowles is the name of the data set, which we already loaded. Here, sex is the variable that we are going to be splitting the data by. And we're going to summarize. We want a correlation, so we want it to, this is the label it's going to put on that column for us. And within that label, we want the correlation between neuroticism and extroversion. So let's run that line. So here's what we have. So it tells us sex first is female or male. That's just the variable. Core, because we told it that's what we wanted it to label that column. So the correlation between neuroticism and extroversion for females is -0.09, but for males it's -0.12. And we can do the same thing, more or less, to ask for covariance, but instead of COR, now we have COV. Let's run that. That gives us the covariance for females and males separately. Okay, so now we want to calculate confidence intervals. We haven't done anything through script yet that gives us confidence intervals. We got them when we did that correlation test with our commander. So we get another library, psychometric. So since this is a new library, let's go back to R. Okay, so we need to install the package. So go to Packages, Install Packages. Choose the right crayon mirror. So I'm going to choose the one in Oregon. And then the name of the package we want is psychometric. Click OK. All right, now go back to RStudio and load that package. And now we want capital C, capital I for confidence interval, R of a correlation. We tell it the correlation, the sample size, and the level of the confidence interval. So we want a 95% confidence interval. Click Run, and it gives us confidence intervals. So the lower limit, 0.85, upper limit, 0.93. We can also compare independent correlations with the psych package. I have installed that already, so I can just load the library. And now here, this is it's the paired R function that we're going to use, and it has several pieces that it needs to know. So for independent correlations, it needs to know what each of the correlations are. So correlation 1 and correlation 2. Put a null value here because we also use this for other purposes, and in this case, there's not a third correlation to deal with. Sample size, 60, and then this N2 is optional, and that's if your different groups have different sample sizes. So if both of your groups have a sample size of 60, then you don't need this N2. But in this case, we have one sample has 60, so this first correlation is based on a sample size of 60, and the second correlation is based on a sample size of 50. So we can run that. And it tells us this is a test of difference between two independent correlations, so that's useful. Gives us a z-score 2.31 and the probability of 0.02. Right, so we can say that these correlations are statistically significantly different from each other. And then finally we can compare dependent correlations, also with the psych package. And now we still use the paired R, but now what we're doing is we're telling it all three of our correlations. So the correlations we want to compare come first, the 0.2 and 0.45, but then the other two variables also have to be correlated. So this is where this 0.15 comes in. This is why we needed null up here, because we didn't have this other correlation to deal with. Sample size is at the end here, 103, and N2 is not an option, because if you're dealing with dependent correlations, you only have one sample size. So we just run that last one. And now this tells us test of difference between two correlated correlations. T, negative 2.13, probability 0.04. So again, these two correlations, 0.20 and 0.45, are statistically significantly different from each other. And of course, we could calculate the confidence intervals of these, which we should do in addition to the significance test if we are going to be reporting this and publishing it. All right, so that's all there is to show you about correlation today in both R Commander and through R syntax.